Hi friends, welcome back to the course. So today we will be doing a problem which was asked in GATE in 2016 or 17. I don't remember it exactly, but this is a 2 mark question. This is a very interesting problem. Again, a real life problem. Moreover, you will be really tested during the while you solve this problem. So whatever concepts you gathered from the last 3 or 4 videos will be put into use. So if you are not following my videos also, this is a question which is asked from the portion of harmonic base excitation. So as usual, I keep telling you this all the time. Please read the question. Please gather as much of information as possible. Please try to draw figures. So pause the video. Do all those things which I just mentioned above earlier, because well begun is half done. So take your time and read the question very in detail. So I hope all of you have read the question. So now let's try to draw a rough schematic of what is actually told in the particular problem. So we have a system like this. So let's say this is the vibrating surface. This is our vibrating surface. So this is vibrating at a frequency of 60 hertz. Then what else is given? Another detail is that this is our instrument, and so the instrument is of mass 1 kg. Moreover, this is the surface that we are talking about. Then let's see, my surface is moving, right? So it is getting excited. My surface is getting excited with an amplitude of, let's say, capital A. Then let's assume my instrument is getting excited. It's getting now, when the base gets excited, the instrument will respond. So the amplitude of the instrument response, let it be capital X. Okay, now the question says that X divided by capital A should be 0.05, or in other words, that means 5%. Or in other words, let's say if my surface or the base is having an amplitude of 100 mm, then my instrument should only see 5 mm. I'm just exaggerating it. I've explained you this earlier. If this is a very precision instrument, I need to ensure that my instrument is not seeing much of vibration. Okay, so that's the whole point of why we need vibration isolators. Clear? Now let's use the concepts what we have learned. Okay, before that, there is one more thing also which is provided in the problem. It is this. Read this. Effect of damping is ignored. That means there is no damper in the system, or damping factor is 0 because C is equal to 0. Okay, and one more thing, there is also one more thing given in the problem. That what is that? In the question they are saying isolation is designed with its natural frequency significantly lesser than 60 hertz. So this is our, let's say, including this is our isolation. So they are saying isolation natural frequency is much less compared to the forcing frequency, or in other words, Omega is our forcing frequency and omega n is the natural frequency of the isolation. This value should be greater than 1 or much greater than 1. See, these are all the things which I could understand or which I could gather out of the problem after reading the problem very carefully. So once again I tell you to read the problem very clearly so that it will give you or it will help you a lot further down the line to solve the problem correctly and efficiently. Now, let's try to recap what we already discussed. So, let me make some space over here. So, if y is excited like this, e raised to I omega t, then my little x will be having a response like this. So A is the amplitude of my base surface excitation, then this capital X of I omega is the amplitude of my instrument response. Now the formula for the magnitude of or the amplitude of the response is given like this: root of 1 plus 2 zeta r whole square divided by root of 1 minus r square plus 2 zeta r whole square. Now we should not forget putting a capital A here. Okay, so this is actually telling if A is the amplitude of the base excitation or the surface excitation, then the amplitude of the response of the instrument will be A times this factor. This factor is called displacement transmissibility. Those things are already been taken care, or those things are already been discussed in my earlier videos. But in this particular problem, since zeta is equal to 0, this expression will be simplified a lot. So finally we will end up with modulus of x of I omega divided by A will be simply root of 1 minus r square whole square. And we know that this particular ratio is how much? It should be 0.05. That means, simple mathematical manipulations, this is root of 1 minus r square whole square is equal to 1 divided by 0.05, that is 20. Am I right? Yes, I'm right. Yes, then that means 1 minus r square whole square is equal to 400. Okay, since see here we need to think. We should not jump into an answer immediately, because given this mathematical expression, there are two possible solutions for this. The one is 1 minus r square is equal to 20. This is the first possible scenario. And the second possible scenario is 1 minus r square is equal to minus 20. Just hold your thought for a while. See, both these equations, doesn't matter whether this is the case or whether this is the case, both of these things will eventually satisfy this equation. So there are two possibilities. Now you tell me, you pause the video for a while and you tell me which is the particular equation that we should take here, or which is physically feasible with the problem that we are solving. Pause the video and come back. I hope you have looked at this. The most possible scenario or physically feasible scenario is this particular equation. Make sense? This won't be the case. 1 minus r square, if r is real, there is no real value of r which will satisfy this equation. So this is the equation which we need to solve. Now everything boils down to just cranking the mathematical wheel. So I will just show you a couple of other steps and then leave it to you to solve the problem and then come with the answer. So it will be r is equal to root 21. R is nothing but omega by omega n is equal to root 21. That means, what is my omega? Omega is 60 hertz. All again remember units. So in omega, I should substitute in radians per second here. So it will be omega will be 60 into 2 pi radians per second. Okay, because that many cycles per second, 60 cycles per second means 60 into 2 pi radians per second, divided by omega n is root k by m is equal to root 21. This units are also again radians per second. Here we know mass of our instrument is 1, so the only unknown is root k. So you can solve for the stiffness of the spring and the value you will get is around 6760 units. Very important, it should be Newton per meter. So you have to always read the question very carefully. So they are asking stiffness in Newton meters. So if they are asking stiffness in Newton per mm, this won't be the value. This should be modified accordingly. So always pay attention to the minute details like this, because doesn't matter even if you reach here, you won't get those 2 marks unless you pay attention to these little details. So I don't want you guys to end up with the negative marks. So that's why I'm keep telling this, pay attention to the units like anything. Thanks for watching the video and all the best.